Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3d hybridization with 3 lone pairs in the main structure. And for this I'm taking the example of tri-iodide ion. So our today's example is tri-iodide ion. That's I3 with a charge of -1. For simplicity, we can write I3 1 negative to be I2 1 negative. Let's make the Lewis structure of tri-iodide ion. That's our first iodine, the second iodine, and the third iodine. Firstly, the iodine belongs to the group number 17 of the periodic table. That means iodine is halogen and it must have 7 electrons in its valence shell. So let's mark 7 electrons around each iodine. I'm marking the electron around the first iodine first. That's the first electron, second electron, third electron, fourth electron, fifth electron, and the sixth electron, and the seventh electron. Now let's talk about the second iodine. That's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, and the seventh electron. Now let's mark the electrons around the third iodine. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Now what's going to happen? First iodine is going to make one covalent bond with the second iodine. Now let's count the number of valence electron around the first iodine after the formation of bond with the second iodine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. That means first electron has attained octet, that is 8 electron in its outermost shell after the formation of one bond with second iodine. Now let's count the number of valence electron for the second iodine after the formation of one bond with the first iodine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means second iodine has also attained octet, that is 8 electron in its valence shell after the formation of one bond with the first iodine. What about the third iodine now? As the first iodine has attained the octet, 8 electrons, second iodine has also attained the octet, that is 8 electrons. So what about the then third iodine, who is having 7 electrons in its valence shell? Now from this part, what's going to happen? We are going to have one extra electron with the second iodine, and this extra electron will make one covalent bond with the third iodine. Now let's count the number of valence electron for the third iodine after the formation of one bond with the extra electron of the second iodine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means third iodine has also attained 8 electron in its valence shell after the formation of one bond with extra electron of the second iodine. Now let's count the number of valence electron for the second iodine again. Now that's the first electron, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and the 10th. So the second iodine has attained 10 electron in its valence shell after the formation of two bonds with the two iodine. Now here you can easily observe that we have added one extra electron in the second iodine, due to which this second iodine will carry a 1 unit negative charge. That's why that's iodide ion I3 1 negative or we can say Ii2 1 negative, because the middle iodine or the second iodine is having one extra electron. Now let's talk about the hybridization. For hybridization, we have to pick the middle iodine because it will act as central atom. So here this iodine, who is having 10 electrons, will be taken to be the central atom because it is forming maximum number of bonds, that is 2 bonds in the main structure. So let's talk about the iodine. Iodine belongs to the group number 17 and period number 5. So its configuration will be 5s2 5p 5. Let's make the orbital diagram for the 5s and 5p. In case of s subshell, we know that we are having only one orbital, that's 5s, and in case of p subshell, we know that we are having 3 degenerate orbitals, the orbitals which are having equal energies, that's 5p. Now in the fifth shell, we are having 5s subshell, 5p subshell, and one more subshell, that's 5d, which is vacant, so I'm marking 0 electrons over here. So let's make the orbitals of the d subshell. In d subshell, we know that we are having 5 degenerate orbitals, the orbitals having equal energies, that's the 5d. Now let's fill the electrons according to the electronic configuration. The 5s is having 2 electrons, so we are going to fill 2 electrons in the 5s orbital. That's the first electron with the spin of plus 1 by 2, and that's the second electron with the spin of minus 1 by 2. Now let's come to the 5p. The 5p is having 5 electrons. So let's fill that 5 electrons according to the Hund's rule. And Hund's rule states that first, in case of degenerate orbitals, firstly all the orbitals will get 1 electron each. After that, pairing will start. So following the Hund's rule, the first electron will be over here, the second electron in the second orbital, and the third electron in the third orbital. Now the degenerate orbitals of 5p have got 1 electron each, so now the pairing will start from the fourth electron. So that's the fourth electron and that's the fifth electron. So we got the electronic configuration for iodine, and that's our ground state. Now let's come to the Lewis structure. The middle iodine is having 1 extra electron, so that means we have to add 1 electron in 5p because the middle iodine was having unit negative charge. So let's mark 1 extra electron over here. Now it's 5p 6 now because of the 1 unit negative charge on the middle iodine or the central iodine. Now let's have a look on the Lewis structure. You can easily see that here iodine is forming the middle iodine, here the middle iodine or central atom is forming 2 covalent bonds. As both of the bonds are single bonds, we can also say that the central iodine is forming 2 sigma bonds. Now for the formation of 2 sigma bonds, the middle iodine must have 2 atomic orbitals containing 1 electron each. Only then that iodine will be eligible for the formation of the 2 sigma bonds. I am repeating it again. For the formation of 2 sigma bonds, the middle iodine must have 2 atomic orbitals containing 1 electron each, which can have the head-on overlap with the atomic orbitals of the another 2 iodines for the formation of 2 sigma bonds. So here what's gonna happen? The 1 electron from 5p is going to be excited from 5p to the 5d orbital. So let's make the orbital diagram again. That's 5s, That's over 5p, and these are the 5 degenerate orbitals of 5d. Let's redistribute the electrons. The 5s was having 2 electrons. Now 5d is having 5 electrons, as one of the electron from 5p have excited to the 5d. So that's the first electron, second, third, fourth, fifth, and one electron have jumped to the 5d orbital. Now that's called the excited state. That's called the excited state. Now let's have a look on the Lewis structure again. The two bonds that has been formed by middle iodine with the side iodines are 2 in number. So here intermixing of atomic orbital will take place, and the atomic orbitals of fifth shell, which are having electrons, will intermix with each other. So here the 1 orbital from 5s, the 3 orbitals from 5p, and 1 orbital from 5d will intermix with each other. That means here is the intermixing of 1 s orbital, 3 p orbitals, and 1 d orbital, and that's our intermixing. The intermixing process of atomic orbitals is called hybridization. Now here total of 5 orbitals have mixed, the 1s, the 3p, and the 1d. So total 5 orbitals have mixed. So that's why we are going to have 5 new hybrid orbitals. We are going to have 5 new hybrid orbitals of equal energies. So you can say that they are also degenerate orbitals. So let's make the 5 new hybrid orbitals. We got the 5 new hybrid cum degenerate orbitals. Now what will be the name of the hybrid orbitals? Here in the intermixing process, we are mixing 1s, 3p, and 1d. So the hybrid orbital will be named as sp3d hybrid orbital. Second one is also again sp3d hybrid orbital. Third one is also sp3d. The fourth one is also sp3d, and the fifth one is also sp3d hybrid orbital. So we are having 20% s character, we are having 20% s character plus 60% p character plus 20% d character per hybrid orbital. So here we are having 20% s character, 60% p character, and 20% d character per hybrid orbital, and in total we got the 5 new hybrid orbitals. Now let's fill the electrons. In the excited state, we can count the electrons. In 5s we are having total of 2 electrons, in 5p we are having total of 5 electrons, and 5d we are having 1 electron. So in total we are having 8 electrons. So in total we are having total of 8 electrons, the 2 in 5s, the 5 in 5p, and the 1 in 5d. So we got total of 8 electrons. So let's fill that 8 electrons in sp3d hybrid orbitals according to the Hund's rule. Now the first electron in first sp3d, the second in second sp3d, the third in third sp3d, fourth in fourth sp3d, fifth in fifth sp3d, sixth electron over here with a spin of -1/2, seventh electron over here with a spin of -1/2, and eighth electron over here with a spin of -1/2. So here we got the 3 sp3d hybrid orbitals which are having 2 electrons, and 2 sp3d hybrid orbitals which are having 1 electron, and that 2 sp3d hybrid orbitals which are having 2 electrons will form the 2 sigma bonds with the another iodine. So firstly, whenever any hybrid orbital is having 2 electrons, that is regarded as lone pair. So first sp3d hybrid orbital is having total of 2 electrons. This will be taken as the lone pair. The second sp3d hybrid orbital is also having 2 electrons, the paired electrons. This will also taken as the lone pair of electrons, and the third sp3d hybrid orbital is also having 2 electrons with the opposite spin. So these 2 electrons are again taken as the lone pair of electrons. Now we are left with 2 sp3d hybrid orbitals which are having 1 electrons. So let's deal with them now. Now we are having 2 more iodines. Let's talk about them now. Iodine. Its configuration is 5s2, 5p, 5. Let's make 5p over here. The p subshell is having total of 3 degenerate orbitals. Here we are having total of 5 electrons. Let's fill them according to Hund's rule. The first electron, second, third, fourth, and the fifth. Now let's take these 2 iodines over here for the formation of sigma bonds. I'm taking this to be the 5p of first iodine. Now the 5p is having 5 electrons, the 1, 2, 3, 4 and the 5. So here we are left with 1 atomic orbital of iodine which is having 1 electron, which is going to have head-on overlap with the sp3d hybrid orbital of the iodide ion. So that's the formation of sigma bond, and that's sigma sp3d and the p. Because this sigma bond has been formed by head-on overlap of the iodide ion. What's iodide ion? That's I negative. So this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of iodide ion with the p orbital of the another iodine. Now let's talk about the second iodine now. That's the 5p of second iodine. 5p of second iodine. Now here also we know that the 5p is having 5 electrons. That's the first electron, second, third, fourth and the fifth. Here we are again left with 1 atomic orbital which is having 1 electron, which is going to have head-on overlap with the sp3d hybrid orbital of iodide ion. So we got the sigma bond which will be named as sigma sp3d p. Why so? Because again this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of iodide ion with the p orbital of the another iodine. So that's all about the hybridization of the tri-iodide ion. Now let's talk about the structure of the tri-iodide ion. Which hybridization we got? We got hybridization to be sp3d. What's the standard structure of sp3d? That's trigonal bipyramidal. That's trigonal, bipyramidal. So I am marking the middle iodine with a charge of -1. Now, how many lone pairs the iodide ion is having? That's 3 lone pairs. You can easily observe that the first lone pair, the second lone pair, and the third lone pair. We got the total of 3 lone pairs in iodide ion. Let's mark them. All the 3 lone pairs will occupy the equatorial position. Now, this middle iodine is making sigma bonds with the another 2 iodine. Let's mark them now. That's the first iodine, and that's the second iodine. For simplicity, I am just imaginarily linking these lone pairs for the better understanding of the structure in the 3 dimensions. So that's the structure of tri-iodide ion. While naming the structure, we have to ignore the lone pairs. So this geometry will not be called as trigonal pyramidal. This geometry will be named as linear. So whenever there is a sp3d hybridization and it is having the 3 lone pairs, then that 3 lone pairs will occupy the equatorial position and we are left with the linear structure. So that's why we will going to call the structure of tri-iodide ion to be the linear. So now let's come to the hybridization again. At last, let's discuss about the energy points. Here we are having 2 endothermic processes. That's the promotion of electron from 5p to the 5d. There will be the consumption of energy. I am writing here is the consumption of promotional energy. Here is the consumption of promotional energy. That is the energy required to promote the electron from 5p to 5d. Now, here is the intermixing of 5 atomic orbitals, the 1s, 3p and 1d. So here also energy is required, and the energy required for intermixing of atomic orbitals is called the hybridization energy. So here I am writing, here is the consumption of hybridization energy. Now let's talk about the formation of the 2 sigma bonds. There is the release of energy. So I am writing the energy is released. The energy is released during the formation of new sigma bonds between hybrid orbitals of iodide ion and atomic orbitals of iodine atoms. The energy released will compensate. So I am writing which will compensate promotional energy as well as hybridization energy. So the 2 energies which were consumed were promotional energy and the hybridization energy, which gets compensated during the energy released by the formation of new sigma bonds between the hybrid orbitals of iodide ion and atomic orbitals of iodine atoms. So that's the reason the formation of tri-iodide ion is chemically feasible or practically possible process. So that's all about hybridization of tri-iodide ion, which came out to be sp3d hybridization with the 3 lone pairs in the structure, and during the naming of the structure we have to ignore the lone pairs, so it came out to be the linear. So that's all about today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.